Hi, everyone. Welcome to the Innovation Evangelist podcast. My name is Tom Raftery, and with me on the show today, I have Mrinal. Mrinal, would you like to introduce yourself?
Hi, Tom. Thank you for having me on the show. As you said, my name is Mrinal Wadhwa. I am CTO at Ockam, and my background is in distributed systems primarily. And over the years, I've worked in spaces like big data and the last 5 years or so in IoT.
Nice. Now, Mrinal, CTO of Ockam. First of all, Ockam, spell that for me, because there are many ways I've seen and heard it spelt.
Right. So we spell it Ockam. But you're right, there are multiple variations on that spelling, but they all refer to Occam as in Occam's razor.
Yes. I was going to ask about that. And what do you guys do at Ockam? Interesting. What would be an example? What would I be doing that I'd want an Ockam?
Currently, there are a lot of different systems that enable you to deploy IoT solutions, right? So if you imagine yourself being a developer of some kind of device that is going to be deployed in the thousands or tens of thousands, and you're developing the device, and at some point in that life cycle of development, you reach a point where you have to think about the identity of the device. It kind of starts with, okay, I need to number this device and give it a 1 or 2 or 3 or 4. But you very quickly realize it needs to be more than a number because when you're delivering data from that device to, let's say, your cloud services, you want to make sure that that data is delivered exactly as the device sent it. So you start thinking about things like checksumming the data. You think about signatures on the data. Basically, how do I prove that the integrity of the data from the device to the server wasn't compromised just because of errors or malicious activity, right? So you very quickly get into the realm of, okay, the unique identity of the device needs to be a cryptographic key and not a number. And so when you're going through this process as a device developer or an IoT solution developer, you reach this point, okay, I need cryptographic keys. And then you very quickly realize, okay, I need unique cryptographic keys for every device. And the reason you need them to be unique is if there was a malicious entity that compromised one device, that malicious entity shouldn't be able to figure out the keys to every device that you ever built just because they compromised one device. So you need them to be unique, and you're producing hypothetically tens of thousands of these things. So you very quickly realize that this is a hard problem. And so typically people will do one of 3 things. They'll do nothing, which is far too common. It is so common, in fact, that we had, a couple of years ago, the Mirai botnet, and then several other botnets that have spawned out of that code base. But essentially, those botnets exist because some developer did the lazy thing of giving a default password to the device, right? And didn't put any kind of key pair in them. So you do nothing. That's one opportunity, one option. In that do nothing bucket, I've also seen scenarios where devices that were previously not connected, but market pressures of competition have led them to become connected. A lot of those teams also do nothing because they're used to not having to think about this, right? So for example, you come across a lot of speaker companies that because of Alexa and other Google Home and all of these things have connected their speakers now, whereas 2 years ago they weren't connected speakers, but they're now connected. However, because there is no guarantee of authenticity of data or integrity of data as it comes back from those speakers to their servers, they have no mechanism to reliably update those speakers. and get a confirmation back that those speakers are not part of a botnet. So these kinds of problems start to emerge. So that's, do nothing is one option. The other option is you do what I did in my previous job, which is you become hyper aware of this problem that I need trustworthy data. And I need data that my customers should be able to rely on. And in my previous job, I was CTO at a company which was focused on smart cities. And in the smart cities use case, we were concerned that this data, the government agencies were relying on a lot of that data. There was emergency response based on a lot of that data. And so we needed to make sure that that data wasn't compromised. And so when you start thinking from that perspective, you either look for something you can buy, or if you can't buy it from the market, you decide to build it. And back in 2014, when we were building that system over at Fiber, which was my last company, there wasn't a solution available in the market. And so we ended up building a full stack ourselves. So don't do anything, build the whole thing yourself, or buy it from someone. And that buy it from someone options over the last 4 years or so has been maturing, and they're typically called IoT platforms. So the problem is IoT platforms as they currently exist in this market are server-only solutions. And so they're typically cloud-based services that are termed platforms for building an IoT solution. They're completely disassociated from the actual device and the manufacturing and the life of that actual device, right? So vendor number one actually builds the device, or you build the device, whereas the server provides the data storage, the key management, the device lifecycle services. The problem that happens is that these two end up being incredibly disconnected because to ensure that your devices have unique keys, you have to be in control of the initial processes that the device goes through. Where, like, for example, when was it given a unique key? How was that key generated? Those types of questions become very difficult for a server-only platform to answer. So to sort of summarize all of these thoughts, essentially, you either do nothing and just ship insecure devices to the market, or you build a fully tightly integrated hardware to software stack yourself, or you buy a software-only stack from one of the IoT platform vendors, and then you buy your hardware from somebody else, and then you try to sort of cobble together a system that you hope works correctly. And that cobbling doesn't, in my experience, work. And the reason it doesn't work is that identity, now I'm talking about the bigger whole of identity, not just the number or the key, but the identity of a device. What is that device made of? What has it been through? Where has it been installed? Where was it built? What software is in it? All of these questions make up the identity of the device. And truly managing the identity of the device must be a well-coordinated process. And I think there's currently gaps in how that's done in the market. And so we're trying to solve that as the very first problem we want to solve. But remember, I said we're focusing on 3 problems: device identity, device trust, and device interoperability. And device identity is just a means to get trustworthy data from devices, reliable data from devices. So IoT devices typically do 2 things. They collect data from the world and send it to your applications, or your applications create an instruction and ask the device to actually execute the instruction, right? In both of those cases, for the device to be reliable or the system to be reliable, you need the assurance that what the device is telling you is what is happening. No, what you think the device is telling you actually originated at the device. You need that assurance, and that assurance cannot be done without key management. So trustworthy data sits on the foundation of reliable identity management and key management. And interoperability is basically a problem that arises from the lack of, in part, a problem that arises from the lack of trustworthy data. So for example, if you buy a device from a Best Buy today, right, and you bring it to your house, you turn it on. Typically, for most smart home devices, it takes you somewhere between 10 to 15 to 20 minutes to get it connected to your smart home, right? The process typically is, unpack the thing, somehow give it your Wi-Fi connection, maybe by scanning a barcode or a QR code, maybe by manually entering some numbers, etc., making sure your Wi-Fi can connect to it, oftentimes in very insecure ways, like giving your Wi-Fi password to your doorbell is probably not a smart thing to do. The reason these clunky processes exist and very manual processes exist is that there is no foundation of identity of either of those two things, the new device you bought and your Wi-Fi router. And there's no notion that exists in the world which can be leveraged for these things to talk to each other in the digital world. So our belief is that if we can build a solid identity foundation for devices, not just consumer devices, even though that's the example I took, but like all devices, even industrial devices, if we can build a solid identity foundation or tools that enables a solid identity foundation, we can layer in a notion of trustworthiness of data that originates in a device. And then once we can do that, then we can simplify a lot of the interoperability problems, remove a lot of manual integration work that ends up happening. And this integration work in your house is 20 minutes. In a big enterprise project is a year, right? Or several months. So we want to eliminate those. Somebody I forget which talk this was, but at one of the IoT conferences, somebody posed a question that really struck home to me. They said, if it takes 20 minutes to turn on one device, how are we going to get to 20 billion, right? It's just, the math doesn't add up. And that made a lot of sense to me. So somehow all of that time lag and costs need to be eliminated. And that's the kind of thing we're trying to do. So why would a developer think about Ockam? Is I think IoT solution developers and device developers are struggling with issues of security and trust and key management. And they're already aware of these issues. It's just that there doesn't exist a good tool to solve these issues for them. And so we want to become that tool.
Okay. Nothing like a bit of ambition, huh?
Right. But I think we're coming from good backgrounds within the team. So the founding team's made up of Matt Gregory, who worked at Microsoft Azure before this, and earlier in his career he was with Heroku, and in the very early days of Weather Underground, which was the API that Weather Channel bought, about a decade ago. So he has had a career in developer platforms. I have had, as I said, a career. I was pretty early on in the IoT market. Have built full stack, large scale IoT systems over the last 5 years, and learned a lot from that. Matt's learned a lot from his platforms and developer tools background. And our third co-founder, Logan, is from the Citigroup and ran analytics and various other financial asset related projects over there. As we get deeper into how Ockam solves those three problems, I'll talk a little bit more about how Logan's background also adds up into this picture. I think we've assembled a team that has the potential to go try and solve this problem.
So, tell me a little bit about that, about how you're solving the problem.
Like I said, we're a collection of tools, but a collection of tools that works well together, right? And so one of the set of tools we're building is tools to make it easy to generate and manage cryptographic keys and assign them to your devices. So for example, traditionally, to manage cryptographic key pairs, if you were, for example, working in a bank or doing that for a large number of websites or web assets, you would maintain what's called a public key infrastructure, or PKI. And this PKI is centrally maintained, and in case of the internet, is maintained in this hierarchy of root certificates. But these certificates, depending on how your hierarchy is organized, are single points of failure. And you may have come across a whole bunch of news items where one certificate authority gets compromised and a whole bunch of websites on the internet get compromised. So typically, these very central key management infrastructures is how people manage key generation and assignment to either in corporate scenarios or the internet, etc. And with the emergence of blockchains, there's emerging this notion called decentralized public key infrastructure. And the idea there is that you move the key management, key assignment, and key rotation, and all of those tasks to a blockchain-based system that eliminates those single points of failures, and also encourages interoperability across lots of parties that are all relying on this blockchain as their source of their root of trust, essentially. So we're building a blockchain decentralized public key infrastructure, but it's also a blockchain that's optimized for various other IoT scenarios, not just IoT, not just identity creation and management or key creation and management. So currently we have tools that help you create and manage identities. We have a blockchain network called the Ockam network, which provides this decentralized public key infrastructure. And it provides some interesting, simple ways to abstract away So the problem that exists with blockchains today and with cryptography is that these are complex things. And so the learning curve is steep if you want to do things the right way. And so even if you figure out where the challenges are in your system design or solution design for an IoT system, solving those challenges is a steep curve because you have to go learn a bunch of really novel things. So our goal is to take all the best practices, take all the learnings I've had from previous deployments, to leverage all the new technology that has become available, one of which is blockchain, but there's also trusted execution environments like SGX, which are very interesting from our perspective. And then there's this very simple idea that has existed for a while called TPM chips, or trusted platform modules, or they're sometimes called crypto modules, but they're pieces of hardware that store your cryptographic key. And so the software in the device never has access to the key. This is a fantastic way of managing and storing keys in devices. However, most devices end up storing keys in the file system. And the reason is that it's hard to deal with the low-level hardware API of a TPM, right? So what we're trying to do is in our tools, which is basically culminated into an SDK. In this SDK, we've abstracted away the complexities of dealing with TPM chips. We've abstracted away the complexities of interacting with a blockchain. We've abstracted away the complexity involved in generating and managing identities, such that with a very simple few lines of code, a developer that understands their solution but doesn't necessarily understand blockchains or cryptography can still build a good quality solution, right? So take away a lot of those barriers.
When you say a few lines of code, few is a very subjective term. Are we talking few thousand, few hundred, few tens, few ones?
I think it remains to be seen, but our current examples get you to a lot with like 10 lines of code, right? So we put some code out today, which I'm sure we'll talk about a little bit, but there are a few examples included in that code that basically around 10 to 20 lines of Golang code. And what they allow you to do is generate an identity and register that identity with this decentralized PKI on the Ockam network, and then create cryptographically signed data as that identity, and write this data also to the blockchain, and in the process.
And do all that in about 10 lines of code?
Yes, correct. Right now, of course, you'll have very application specific logic. Like developers of like certain devices or solutions will have very application specific logic that we can't necessarily abstract away. But the assumption here is that they understand that application logic. What we're trying to hide is the underlying, the infrastructure, right? We're just hiding the infrastructure and giving them simple APIs to build their solution.
Yeah, stuff that they don't want or need to know anything about.
Right. However, cannot completely ignore, right? Which is what they currently do, right? And they just ignore that layer.
I mean, if I'm a web developer, I don't want to need to know how to set up a web server.
Yeah, exactly. Right, exactly.
But it has to be there. But I shouldn't have to learn how to do IIS or any of that stuff, or Linux or any of that. I just want to code a website.
And similarly, you just want to build a device and cool thing that does something nice, right? And you want to do it quickly. So yeah, that's exactly the idea.
We want to talk a little bit about the code. This is going to be difficult for anyone who's just listening to this in audio, but we're also recording this in video. I'll have some links to screenshots in the description of this podcast for anyone who's interested in checking out the code. But Mrinal, can you show us some of the code now? Share your screen.
Absolutely. So, all right. So what we have here is what looks like about 50 lines of Golang code. But Golang's a little bit verbose. It asks you to sort of share, like deal with errors explicitly and things like that. But the actual meat of the code is, this main function with these lines here in the middle. So I'll step through this. But before I jump in, let me set the context a little bit. So first of all, this is first of many programming languages we will support. In this case, this is Go because the core of our system is also written in Go, and so it was easier for us to do Go as the first language option. But we plan to do this in a lot of different languages, and we're also looking for contributors and partners who may want to implement specific languages.
So we should say, because we haven't said this explicitly yet, but we should say that today, your time, yesterday my time, because we're in different time zones, you guys made this available on GitHub.
That's correct. So we open sourced the Ockam repository on GitHub. This repository currently contains code, two things primarily. One is a command line tool that allows you to interact with the Ockam network, which is Ockam test network, which is publicly available. And it includes this Go package that allows you to write programs that also interact with the Ockam test network. The code is open source under the Apache license. It's a fairly open license, or actually very open license. And our hope is that we can encourage contributions and collaboration and discussion around the project and get as many people excited about it as possible. All right, so let's look at this. So the very first line of code is basically trying to say, hey, how do I connect to the rest of the network? So you're writing a new program. You're in the first line of main, and the first thing you need to do is connect to the network. The way you do that is by creating a new local node. And you tell this local node, here's how you can discover more peer nodes on the network. In the test setup, the way the discovery works is via DNS, but over time we will have lots of different discovery mechanisms because we're also trying to decentralize discovery and participation on this network. But for the moment, it works via DNS entries. So this new node, however, that just got created is a very lightweight node on the blockchain network. So a confusion that you commonly encounter about blockchain systems is that to be a node on a blockchain, you have to download the entire data that makes up the blockchain, or at the very least, download all the headers of all the blocks that make up the blockchain. This is true for the two very popular implementations of blockchains that exist, which is Bitcoin and Ethereum. In fact, in case of Ethereum, it's with their new Casper design, it's actually changing a lot. But traditionally, over the last several years, since Bitcoin and Ethereum have existed, both of them, if you want to be a node on that network, you need to download all of the data that is on the blockchain. The reason for this is that what you're looking for as a decentralized participant on a blockchain is you're looking for a guarantee that when you write some data to the blockchain, that data in fact was written. And the way you get that guarantee is by tracking all the blocks in sequence and then looking for the next block that's created to ensure that it is part of that same sequence of blocks that are being produced on the chain and are going through the consensus process. However, in our case, because we were trying to be a blockchain that IoT devices can participate on, we cannot afford for most IoT devices cannot afford to download large amounts of data. They can afford to download very tiny amounts of data typically. They don't have a lot of storage. It's not uncommon for them to not even have a writable file system. They especially don't have a lot of network bandwidth or battery power to communicate over the network. So what we wanted to create was a light node. And the way we've done that is by switching the consensus architecture of our blockchain from being a availability-oriented blockchain, which is what Ethereum and Bitcoin are, to a consistency-oriented blockchain, which is what we are. And there are some other examples of that happening in some newer systems as well. But because we're a consistency-oriented blockchain, we get 100% finality of the data that is written to the blockchain within somewhere between 1 to 3 seconds for every block. And the reason this is important is because this is 100% final, and it's proven by the fact that 2/3 majority of validators have signed a particular block, you don't need to track all the blocks, and you don't need to track all the headers. And that has massive implications for IoT, not only in terms of data storage and data downloads over the network, but also in terms of like offline and occasionally connected devices. So in a scenario where you're communicating with, let's say, Ethereum as it stands today, if you had a phone that is communicating with Ethereum and you turned off the phone, let's say tonight, and turned it back tomorrow morning, your phone would have to download 20 to 30 megabytes of data before it can be sure that the new data it's writing to the chain is actually being written to the chain. Whereas in our case, when the device turns on in the morning, all it would have to do is download the latest block header, which is less than a kilobyte, typically a few hundred bytes. And if that block header has been signed by the same validator set that was active when the device went offline last night, it can just proceed from there. And it is in sync with the chain, and it has 100% guarantee that it is in sync with the chain, which was important for our design. So to sum up, we've designed the network with the typical concerns of an IoT device in mind. All right, so moving on, you create this lightweight node. You sync it with the network, which basically means download the latest block header, and then you figure out the chain you're connected to. And this is just the basic connection, hello world, to the network, right? At this point, you can print out the chain ID that you're connected to. This would print out the chain ID of our live Ockam test network currently. And this is where it gets more interesting. So the next thing you do is you generate a signer. And a signer is basically a key pair that you use for signing data that you produce from your device. And the way this signer is implemented is that it leverages interfaces in Go and abstracts away the implementation of the signer from the interface of the signer. And the benefit of that is that we can plug in various implementations of the signer without affecting the rest of your application. So what that means is that you can either have a file system-based ED25519 key, which is what I have in this particular example, or you could have a specialized TPM model 123, right, or ARM TPM or whatever, right? You have a specialized hardware, and you can implement a signer for that hardware, and now your keys can live in the hardware, and they don't have to be exposed out to the operating system. And all signing can happen in hardware. So this was very important to our design as well, because we wanted to abstract away the specificity of hardware away from the application level code. And we do that in multiple places. Interaction with signers or key pairs is one example, but also interaction over the network is another example, or over the internet is another example. So it's possible that a lot of IoT devices aren't actually on the internet, even though we call them Internet of Things devices. They don't have an IP. They connect to the internet over radio via gateway, right? And so in those scenarios, we want to make it possible for your application code to stay the same. All you do is plug in a different communication mechanism instead of HTTP, right? You may plug in MQTT if that's what's available, or you may plug in a specialized radio protocol if that's what's available, right? Okay, so we created a signer, and the next thing we do is we create a entity. So an entity is our abstraction for everything that is represented on the Ockam network. So you create an entity, you give it some metadata or some attributes, and you tell it that this entity has this signer, which we created in the previous step. What this does is this creation of the entity, what it does is it creates a DID, or a decentralized ID, that represents this thing. In this particular example, it's a temperature sensor. So this temperature sensor gets a decentralized ID that represents it. And decentralized IDs are a in development standard that is being developed under the W3C. And what this decentralized identity standard allows us to do is basically implement that decentralized public key infrastructure that we talked about earlier, and decentralize the management of identity. So currently, if you register yourself to a Google account, Google has control over that username. Whereas in case of the implementation of decentralized IDs, the blockchain is where the data about the ID lives, and anybody is free to generate that ID and register it to the network or to the PKI. And that way, there's no central party in charge of whether or not a device is allowed to be on a network or not, right? And you can put in authorization controls on top of it as part of your application, but at the core, decentralized IDs are completely decentralized. And so when you create this entity, it gets a decentralized ID that is based on the public key of the signer that you just gave it. The next thing you do is you create what's called a registration claim. The word claim here refers to another open standard that's being developed under W3C called verifiable claims, which is basically standardization of the idea that these decentralized IDs or decentralized identities should be able to cryptographically sign the data they produce. So what's happening in this line number 44 over here is that the temperature sensor is telling the Ockam chain, hey, register me to the Ockam chain. And the message it sends is signed by the temperature sensor. And so what that does is forever associates this signer's key with, or public key with, the temperature sensor. And then this registration claim is written to the chain. You can run proofs against whether or not it was committed. And remember, because this gets committed in 1 to 3 seconds, this confirmation can be very quick. The device can either wait for the 1 second, but in a lot of IoT scenarios, I've also seen that 1 second wait is also too long for battery consumption wise. So what it can do is the next time, if it's a sensing device that found some interesting piece of information, it sends it to the network and goes back to sleep. But then the next time it has something interesting to say, it connects to the network, checks if its last message was written to the network. If not, it can try that again, and also sends the new message, right? So a lot of those variations are feasible. But okay, to quickly summarize, we did 3 steps. We connected with the network, we created a signer, we created an entity, and then we registered the entity. So 4 steps, right? But in these 4 steps, you got a framework to create an application that has unique cryptographic keys for every device, and has and produces always produces cryptographically signed data, which means that all data that lives now in your IoT solution is signed by the source of that data. And that automatically sets you up for a lot more trustworthy data. So that was sort of the point of my example. And I'll quickly show one more line, which is a custom data claim. So even though in that example, we were looking at a registration claim, you can have custom data. So the temperature sensor could make a temperature claim and add a temperature value, in this case, 100, to that temperature claim. And then assign and set up an issuer and a subject of the claim. This issuer is the sensor that created the claim, but the subject can be something else. For example, the subject can be this room, and this room can have a DID associated with it. And you can say that the temperature sensor is making a claim about this room. And this claim is signed by the temperature sensor. However, a higher level application may or may not want to trust this temperature sensor. And so this decision of how you come up with what data you trust becomes a higher level trust scoring algorithm that can be implemented on top of this basic signed log of claims that is stored in a blockchain. Okay, I'll stop here. I know it's a lot of information to sort of dive into, very quick. But I'll stop here and we can discuss more.
I guess let's talk. Let's back out of the code stuff that we were talking about, the technical stuff we were talking about, and let's get to some of the business stuff. What's the business model for Ockam? You said you're building tools, and you said you've put them up on GitHub. How are you guys going to make money from this?
So there are things we can look at. So in the blockchain world, especially for example Ethereum, there's this model called the gas model, which is basically a measurement of computation that you run on the blockchain, and you pay for the amount of computation you run. This is not a completely unfamiliar model to enterprises as well. This is what serverless computation looks like, right? So we will likely implement, we are implementing a serverless compute type implementation where you get charged for the amount of computation you use on the network. And the other thing we're doing is we're building higher level products. So the core infrastructure is make sure every device in the world has a reliable cryptographic identity, and make sure every device and its life can be recorded in signed cryptographic claims or cryptographically signed claims, and then enable these entity registrations that are claims to include some metadata about the device. This metadata can be just the name of the manufacturer, or this metadata can be, I am a temperature sensor. If you want me, or I am a light switch controller. If you want me to turn on and off, send me a claim at this URL, and sign it with your private key. So I'll look at my authorized keys, and if you're authorized, I will turn on and off, right? That can be encoded in very simple metadata, somewhat on the lines of the old service-oriented self-discovery services world. And I know WSDL is nightmarish image for a lot of us. I've been through the pain of dealing with WSDLs, but WSDLs had a very nice attractiveness to them, which was that they were self-descriptive web services, right? And I think there's an opportunity to revive some of those ideas, but let go a lot of the complexity that the whole SOA thing brought with it. So if there's a self-descriptive metadata that lives on the chain that is signed by the device, saying if you want to send me a message, this is the service endpoint and this is the structure of the data you should send it in, then suddenly you get the interoperability layer, because device number one publishes this information to the chain, and device number two can discover this information from the chain without ever having some kind of manual pre-configuration. And so two devices can encounter each other in the real world and discover how to talk to each other and do an exchange. So to your question of how do we make money, we're enabling a serverless compute type of model on the system to enable applications to not worry about the infrastructure and still build their applications. And we're building these higher level products around higher level products that sit on this foundation of identity, trust, and interoperability that we want enabled for everybody.
We better wrap up because we've gone quite long. No worries. Last question. If people want to check out Ockam, check out the Ockam network, where do they start? What's the best way to kick off their journey on this?
Okay, so we are Ockam, OCKAM -network/Ockam on GitHub. That's where our open source repository is. There are examples there. There's a README to help you get started. The tools will work with the live Ockam test network. The test network status page is ockam.network, HTTP Ockam network. or Ockam.network, and you can figure out what the status of the network is. And other than that, on that GitHub page, there's also a Slack link, which is our open source community Slack that we encourage everybody to join, and our entire team's there all the time. And we'd love to have conversations and learn about use cases.
Super, super. I'll put some of those links into the description of this podcast as well, and in the video, because I'll be putting it up on YouTube as well. So thank you for that. Mrinal, that's been really interesting, real deep dive as well. So for anyone who is more technically oriented than I am, they'll get a lot out of this, I think. Best of luck with it, and I hope it goes really well for you guys.
Thank you so much, and thank you for having me, and thank you for letting us do this conversation.
Cool.